going to be 180 degree change. And make sure it goes downward. Even if you start at minus 90. So if we think about that for a moment. This is our double pole, P1, double, 0, minus 90, minus 180. Well, if we're at minus 90 for less than that, where do we go? Well, if we cross a double pole, we're going to do something like this. But we typically don't draw that below minus 180. That would wrap around from the top. And it would be something like this. Just to keep it on a full circle. You could draw this. I mean, mathematically it's correct. You can draw it from minus 90 to minus 270. That's okay. The calculator will spit out the right numbers. You can put 5 pi in your calculator and you'll get the same value as if you put pi in your calculator. So technically this is correct, but if we do have a plot where things are drawn wrapped like this, well, this is 90 degrees downward, and that's still going downward by another 90 degrees, wrapping around the circle to the positive side. We've seen that before. So nothing new particularly here. On the other hand, underdamped, what happens? A more rapid change. Of 180 degrees. So we still go from some value, 90 or minus 90 in this case. We would still have a change of 180 degrees downward. So it's not a real pole, yes, but it's still a double pole with a resonant frequency of some value, omega naught. If it's a double pole and we cross it, what happens? Our phase changes by 180 degrees. And we could think of an extreme example. So we could say H of S equals omega naught squared, S squared plus 2 alpha S plus omega naught squared. And if we look at the critically damped case, just for reference, because it is a nice reference for us, critically damped being the border between overdamped and underdamped. Well, this winds up being omega naught over S plus omega naught, nothing there, squared, right? Technically, that's what critically damped is, because 2 alpha, or alpha equals omega naught, and so we can factor that out and just write this as the square. And so if we look at this in our phase plot, what does our phase plot look like? And I should probably use blue paper. If this is our critically damped case, there's omega naught phase. There's 0, 90, 180, minus 90, minus 180. Well, for omega small, what's the phase of this? For omega much, much less than omega naught, or S less than omega naught, what's the phase? Something we should be able to do by inspection. 0. So far away, we have 0. And if this is critically damped, our change of phase of 180 degrees over 2 decades is realistic. And we do something like that. So there's our nice phase plot. Critically damped, and we could, if it really bothers you, you can throw a little curvature in there just to make it prettier. Well, that's the critically damped case, where our damping ratio is 1. We could go to the extreme. What's the most underdamped case in the world? Yeah, which is the damping ratio of 0, which implies alpha equals 0. So we wind up with h of s equals omega naught squared over s squared plus omega naught squared. Can you build something like this? Yeah, kind of, you can. We'll look at that in a second. If we think about this for a moment, well, S equals j omega, and you said that all along, so we can plug in h of j omega equals omega naught squared minus omega squared plus omega naught squared. Ignoring omega naught for a moment, if we look at this from a phase point of view, for omega less than omega naught, angle of h of j omega is what? Well, if this is less than this, what's the sign of the denominator? It's still a real value. It's positive. If this is less than this, omega less than omega naught, angle of h of j omega naught equals 0. And it doesn't matter how close omega is to omega naught, right? I mean, omega naught could be 10 to the 3, and we could be saying 999.9999999, and that still gives us an angle of 0. On the other hand, omega naught less than omega, what's the angle of h of j omega naught now? Well, this is slightly smaller than this. And now we get minus 180 degrees. So what happens when we cross omega naught in this case? What does our phase response look like? So here is our critically damped case. With the damping ratio equal to 1, alpha equals omega naught. 0, 90, 180, minus 90, minus 180, omega naught. For any number less than omega naught, what's our angle? 0. For any number larger than omega naught, what's our angle? 180. So what does our response look like? And that's actually what happens. As we underdamp more and more, this gets steeper and steeper until you reach this limit. And so that's what I meant when I wrote this down, a more rapid change of 180 degrees as we underdamp up to the upper limit where we're as maximally underdamped as we can be. In other words, we remove the resistor and we have an infinitely steep change of 180 degrees crossing our omega naught. Conceptually, I want you to understand this rigorously. You know, there's no quick and easy way of finding out how steep this slope is, other than qualitatively saying, if it's strongly underdamped, it's pretty darn steep. If it's weakly underdamped, it's pretty close to the critical response. So, somewhere in between there. You plug in numbers if you feel like being specific, but here's our two limits. Maximally underdamped, critically damped. So somewhere in between. Coming back to this for a second, what does this circuit look like? Were we to build it? How could you build it? I just said it a second ago. Take out the resistor. What happens if you take out the resistor? Well, at resonant frequency, what's true about the impedance of the capacitor and the impedance of the inductor? They're equal and opposite, so they sum to. So how much current do we have in this? Effectively, you create a short circuit from the impedance point of view. Current goes to infinity, and effectively what you have is these guys trading infinite energy back and forth between them. Now, practically, what really happens? I mean, you can go on Wednesday and you can build this circuit. I'm not sure it's a good thing for your discovery board, but practically, what will happen? I mean, remember, this is a model. What are we neglecting in this model? Yeah, the wire resistance, the internal resistance of the discovery board itself, which is actually not zero. So the internal source of the discovery board has a resistance associated with it. So, but I think even if you built this, it may cause problems for your discovery board. It may current limit. Yeah.
Discovery board has a block resistance at the time.
Yeah, but it's still going to only supply so much current. That current's got to come from somewhere. So you can build it, but this is actually kind of a practical thing that people do. You build resonators. So another example of resonance is lasing. So lasers essentially kind of bounce back and forth in phase, and so effectively it's a similar type of mathematical behavior. So bouncing back and forth, gaining energy until you can build something that puts out some light, I suppose. All right. So that was a brief discussion on phase. Any questions on that? Everybody comfortable? So, taking a look at some of the design problems for homework, or what we have in the handout here. These are loosely called design problems. You have a set of specs. Build the circuit. So the first set of specs, we have something that looks along the line, a low pass filter, a stop band, roll off. What was it? 60. And at the cutoff frequency, minus 9 dB relative to the stop band, relative to the pass band. How could you build this? I didn't quite hear that. That's one way of doing it, 3 first order filters. So what do we need in between though? Isolation op amps. Voltage follow. So voltage follow. And if we look at this, H1 of S, doing it with stages, equals 1 over RC, S plus 1 over RC. H2 of S is just 1. I realize it's the identity, but it's worth writing down. H3 of S, 1 over RC, S plus 1 over RC. H3 of S equals 1, H4, so H5 of S, 1 over RC, S plus 1 over RC. Why does this work? Well, this implies a triple pole. So we have 60 dB roll-off. We recognize that requires a triple pole at our corner frequency or cutoff frequency. Our corner frequency is a minus 9 dB point. If we have a triple pole, first order circuits by default, by their life, give minus 3 dB per pole. 3 first order circuits then correlates to minus 9 dB. And so we can plot something like this. It probably would have been a good idea to plot first. There's 60 dB roll-off. And there's our minus 9 dB. I'm calling this a low-pass filter, but we've kind of violated that 3 dB range for our passband. That's okay, I said that was a convention, it's not a fact of life. Then we can pick here, R equals 1K. And where was our cutoff frequency? Left off that little bit of information. 10 to the 8. If R is 1K, C 10 to the minus 11. Is that a reasonable value for a capacitor? Yeah, sure. That's reasonable. It's only when you get really big or really, really small that you start to have to be a little bit more careful. But picofarads, reasonable value for capacitors. Is that the only way to build this circuit? No. Could we do it with inductors?
Yeah.
If I have an inductor stage, what do I measure my stage across? What's the output of that stage? It's the resistor. So if we're going to build this with inductors, we do something along the lines measuring across the resistor. Does everybody agree with that? Anybody not sure where that comes from? What else could we do? What if I only gave you one op amp? Could you build this? How would you build it with only one op amp? Critically damped. So with just one op amp, you can still do an RC stage. RC, maybe we'll call that R1C1 now. And we still want to measure across the capacitor. There's the second order circuit. R2, C2, just call it L2 for consistency. And how do we pick values here? Well, this is still has to be an omega C equals 10 to the 8. What's true about this? What's that? Oh, flip my labels. Thanks. L and C, yes. The drawing was right, the letters were wrong. What can we say about our second order circuit? What do we want to do for this particular spec? How should we characterize that second order circuit? What sort of damping do we have?
Critical.
It's going to be critically damped. And what do we know about our critically damped circuit? Omega naught equals 10 to the 8. So those are our two design criteria. Omega naught equals 10 to the 8. This is critically damped based on our specs. Which means alpha also equals 10 to the 8. Well, one thing to point out here, how many constraint equations do I have here? There's one. So what happens? I have two unknowns. How do I start with the design process? Maybe I should have mentioned this earlier. Make R equals 1. Yeah. That's probably not the best choice, but you pick one. Doesn't even matter which one you pick. You can pick the R, you can pick the C, you pick a value. Do the same thing in the RLC circuit. We only have two constraints. We have an omega naught that's 10 to the 8, and an alpha that's 10 to the 8. But we have three terms. So here, just to write that out in detail, 1 over R1 equals 10 to the 8. Here we have omega naught equals L2 C2 equals 10 to the 8, and alpha equals R2 over L2, 1/2 equals 10 to the 8. So 10 to the 8. Two values, one equation. Pick one value. Three values or three components. If you want, components sounds better than values. Three components, two equations. Pick one component. Yeah.
Are there any like advantages to keeping a large number or small number?
Well, there's a realistic issue. So if you picked 1 ohm, in mathematics, I don't care if you do this on the exam, but kind of be aware, why would picking 1 ohm a problem? Yes, I saw a couple questions just there. So we'll come back, or I'll answer your questions. But what would be a problem with picking 1 ohm? Not sure I quite heard. I mean, maybe what you said was. Well, I think you're saying where I'm headed is the wires in the circuit can be about 1 ohm. So your resistance value is in the noise of the circuit, so to speak, in that your resistance is comparable to the resistances that we're ignoring. And so that's not valid. So it wouldn't, you would shift your resonant frequency. Yeah. What's that?
Should it be omega naught equals the square?
Oh, square root, yeah. Thanks. Sure. Do you have the same question? Yeah, square root. Of course. So on the flip side, well, what about picking, 100 meg? Why not pick 100 meg? Yeah.
You'll have less current, so it'll be more susceptible to noise.
That's a factor, but you also wind up, if you pick an omega or an R equals 100 meg, what's that going to mean for your inductance? And so those other components are also going to be affected by your choice of R. And so whether, if you pick an R that's, 10 to the 9, something like that, giga-ohm resistor, you can get giga-ohm resistors. Well, if we picked an R that was 10 to the 9, what is L going to be for us? 5 Henry. So if R is 10 to the 9, if you pick a giga-ohm, L is a 5 Henry inductor. Can you get a 5 Henry inductor?
Yeah.
Yeah, if you went down to the substation and pulled one off one of their poles. You could probably have field trip. You could also wind up in jail because they're really going after people that steal copper now. Which is a big thing actually in power. So, actually, I think they're starting to go after the metal traders, the waste traders, for buying copper. It's such a big problem, theft of copper. That was something that a project I worked on a few years ago. Is they asked us if we had a way of determining if the grounding grid in the substation, which is just a bunch of copper lines, 3 or 4 or 10 feet down under the earth, if we had a way of detecting if that copper was being pulled out, because they said people come with trucks, find an accessible point on the copper, hook up their winch, and just start reeling it in. And I guess it's that valuable if you get a few hundred pounds of it, and maybe you don't got to work the rest of the month. So 5-Henry inductors are typically fairly big. You can spend a lot of money and get them smaller, but more often than not, they're big. So there are practical considerations, certainly values that we think about. Picofarad for capacitor up to 1 millifarad, very easy in a laboratory setting. Outside of that, you can spend a little bit more money to get parts, but as you get into like the 10 farad range or something like that, they're pricey and they're expensive. On the same token, if you're trying to develop capacitors that are very small, 10 to the minus 15, it takes precision machining, precision calibration. So typically, you don't actually want to build inductors. Most of the time, most circuits avoid inductors outside of big power engineering systems. On the small scale, inductors are problematic. Some of the more recent, by recent I mean last 20 years, 10 years, substrate inductors are interesting and they're becoming more useful. They also have a lot of parasitic capacitance associated with it. So any other questions on this? You can find values here. We have our defining equations, pick a resistor, pick an inductor. In a test setting, again, I don't care what you pick, as long as it's consistent, though more likely than not, or it's a better idea to know that the values you're using are reasonable values. So, same type of problem, but now we're going to do low pass filter, cut off at 10 to the 8, 60 dB roll off. At omega cutoff, omega C, minus 4.5 dB. How do we build this relative to the pass band? Now we have less choices. So, still at omega C, what must be true about omega C? We go from 0 dB to 60 dB roll off. Effectively, what must that corner frequency be? Well, that's getting ahead. I mean, what must be true about the poles at that corner? It's still a triple pole, right? We have a change of minus 60 dB in our slope, 0 to minus 60. So that still must be a triple pole. Effectively a triple pole. At omega equals 10 to the 8. Well, this is a triple pole. How do we do that? Well, what are we stuck with? What type of circuit are we going to build? And we just did it a minute ago. Spice typically doesn't take very long to collect the data, and certainly by all means go out and do something more interesting than sit around in 4201. Be that a seminar or anything else for that one. Any other questions on anything? Homework questions, administrative questions, exam 3 questions? Moving forward. Everybody's good? Life is well? You got lots of sun and exercise last weekend? Okay, so kind of just to revisit our concepts. With our first order circuits, RC or RL circuits. We can build a high pass filter or a low pass filter per stage. So if we have multi-stage circuits, we can construct more sophisticated things, but high pass filter, low pass filter per stage only. We can cascade using isolation amplifiers and get circuits that are more complicated. We can build a band pass filter. Using 2 stages. A high pass filter and then a low pass filter. Isolation. And then a low pass filter. And then output. So we can construct anything with first order filters. We can construct a high pass filter. We can construct a higher order low pass filter. We can construct a band pass filter. But we are limited with real roots, or real poles. Real poles only. And what's the price that we pay using real poles only? Well, we don't get a very flat pass band. Not as flat as it could be. Put quotes around flat. For example, if we just have a single low pass filter, in and out, then our circuit, our pass band looks something like that, and we have a minus 3 dB correction right there. And we can fit 20 dB roll off and a 0 dB pass band. Well, to achieve a better stop band, so stop band not very steep, we can do 2 cascaded first order filters. And now where are we? Well, we have a steeper roll-off. Pretend that's steeper, 40 dB roll-off. But now we're down at minus 6 dB. And so our pass band, we kind of exaggerate things. Here's our pass band here, mostly flat with a little curve. Here's our pass band here, and we really kind of bend. All right, that's way exaggerated. But it's getting the message across. Our pass band attenuates more. And we can keep going, get higher, more steep roll off, but at a price. We can look at 3 LPF times 3, and then we get something that's minus 9 dB. And our pass band looks something like that. So even worse. Again, that's a little exaggerated, of course. But each pole we add to get that better roll off, we lose flatness in our pass band. On the other hand, we can look at our second order circuits. So second order. And for us, we're just looking at RLC circuits. And we can do the same construction with critically damping the circuit. Critically damping is equivalent to cascaded first order circuits. Our poles are real. We're going to have a minus 6 dB, all that. So it's like 2 cascaded first order circuits in a row. Over damping also is equivalent to cascading first order circuits. I guess you save yourself an amplifier, so you save yourself some footprint. you pay for that again with the inductor. But neither of these, in terms of achieving a more flat passband, are doing anything for you. So, critically damped, we're going to have a -6 dB correction. Over damped, we're going to have two -3 dB corrections at two different poles. Under damping, on the other hand, can achieve a flatter passband. With the same stopping. And so that's our ultimate goal. In the design of circuits, if you looked up circuits at all or read the book at all, you saw Chebyshev circuits or Butterworth filters or Chebyshev filters, Butterworth filters. They all revolve around various under-damping cases. Sometimes there's real holes in the higher order circuit, but they also have under-damped complex conjugate pairs of holes. So this is really kind of the magic with the second order circuits. You do things with under-damping. And so just a review of what we looked at there. A little bit of a summary with our second order circuits. Second order Bode plot summary. Overdamped. Find the poles. Identify regions. And build straight line approximation. And we've done this already. We added a little bit more detail in our notes here. But essentially this was the homework 8-way. You know, find the poles and zeros if it's a more complicated measurement. Find the poles and the zeros, arrange them sequentially, find the regions in between. In each region, get the approximate transfer function. From that approximate transfer function, build a straight line approximation. We've done that a lot. Critically damped, it's the same. Except you're looking at find the double pole. Identify the regions. And then again, build a straight line approximation. So nothing's changed here. Same thing we would do with cascaded first order circuits. We do with the overdamp and the critically damped case. We could identify the transfer function here as well. So, underdamped case is always a little bit different. And historically, where students have struggled a little bit. In the underdamped case, we look at two further kind of smaller cases. We can look at the low pass filter and the high pass filter. And here, we start with the critically damped case. And so the critically damped case has a cutoff frequency, omega c, at omega naught. So the critically damped cutoff frequency is omega naught. And we know that alpha equals omega naught. That's our cutoff frequency. So we start with that case. We build our straight line approximation. Maybe we could say sketch. You know, dash lines or something. Don't quite fill in. And again, in the circuit is not relevant, but, so if we're looking at a low pass filter, here's our straight line approximation. This is 40 dB roll off. There's our pass band, and that's omega C. So right at that corner there, that's omega C. And now, far away from the cutoff or resonant frequency, we can fill this in. So away from the resonant frequency, that's asymptotically correct. Away from omega naught, asymptotically correct. At omega naught, we can add a correction. Oh, sorry. Away from omega naught, we're asymptotically correct, which is what I have drawn here. At omega naught, we can add a correction. At omega naught, 20 log of h of j omega naught equals, give myself enough room, 20 log 1/2 times the damping ratio. And there's our correction. Now it doesn't necessarily mean you're above 0. Since we're talking about underdamped, there's our minus 6 dB point for our critically damped case. Our correction is going to be somewhere greater than minus 6 dB. Relative to the pass band. Oh, no? Okay, thanks. What's that? Yes. 20 log 1/2 times the damping ratio. Which will be greater than minus 6 dB relative to the pass band. So that's not an absolute value. That's relative to the pass band. If you're strongly underdamped, then you're going to actually wind up being way up here. And your curve will do something like this. So as you underdamp that more and more, this point moves up. And that's it. You still start with the critically damped case. You draw your asymptotes far away from that omega naught. That asymptote's correct. And then you can find this point directly by just using this expression. That comes out of the transfer function. We did that last week. We obtained that expression. And so this point larger than minus 6 dB. A couple special cases again. In this case, the damping coefficient equals 1/2. Well, in this case, 20 log of h of j omega naught equals 0. So that's 0 dB relative to the pass band. So if we have a gain term in here, everything shifts off as well. That's 0 dB relative to the pass band, and that will be right there, which gives us a nice corner, supposedly, something along that line. And so this is where we want to be. So in our design problems, if we're trying to make a flatter pass band, we need to have a second order circuit. As a side question, so if I just draw a low pass filter, it looks something like this. And I tell you this is 60 dB roll off. What has to be true about this point, effectively? If that's a 60 dB roll off, we pass the pole, effectively, what type of pole is this? It's a triple pole. What type of correction can we have there? Well, if it was all first order circuits, what would the correction be? -9. If I did something along the lines where I had a second order circuit with a damping ratio of 1/2, what correction would I have there? -3. So the second order circuit would give us 0 dB relative to the passband, but the first order circuit that we also need to give us the triple pole, -3 dB. So we would add things there. So this slope kind of tells you information about what's going on at this corner, this cutoff frequency. And again, you can underdamp more, but then things start to get a little bit ugly and you stop building a real good filter there. And just for our other item of interest, and the classic value, -3 dB. So that brings us into the 3 dB variation I talked about, where the passband is a variation of 3 dB with a little bit of hand waving. That's a convention that's been kind of agreed upon, not an absolute condition, but this gives us a passband. And then the roll off, that's a red knot. Then this is a 3 dB variation, which is one of our values of interest, without going above 0 dB on the line. So one of the prices we pay here is there is a little bit of a bump right before the resonant frequency. If this is 1/2, we actually go up and then kind of come down. And so we gain a little bit. There's a point where we actually have effectively kind of a gain term, where the output is larger than the input. Now that said, that was the low pass filter and the high pass filter. So again, start with the critically damped case, sketch a straight line approximation. Away from omega naught, it does go to that straight line approximation. And then find a correction at omega naught that gives us kind of a way to sketch it, a way to look at it. The band pass filter, on the other hand, is a little bit more complicated. So underdamped, still the same category. We're going to have an inverted V. So asymptotes, in this case, take the form of an inverted V. Specifically, they'll look something like this. And so we can take a little Bode plot, and our asymptotes will be something like this. There's our dashed line. And each of these are 20 dB roll-off. We're just talking about a second order filter. 20 dB roll-off and 20 dB roll-off. And again, as we get far away from omega naught, this is accurate. We can fill that in. Where things get a little bit more complicated is the other thing to note. At omega naught, 20 log h of j omega naught equals 0 dB. Always. So I didn't draw any scale here on this. I didn't give any units. So at the resonant frequency, the bandpass response for our second order circuits is always 0 dB. that hits the 0 dB line. And again, this is assuming there's no amplifier stage, no gain stage. So just a second order circuit by itself. So that's a 0 dB point somewhere along this resonant frequency. Where is it located? The vertex of the inverted V that point is 20 log of H of J omega naught away from 0 dB, or more specifically, we're out of power. That was kind of fun. Or 20 log of 2 times the damping ratio. So it can be both above or below 0 dB, but if there's our point, ultimately this is a 0 dB point, and our vertex this distance here is 20 log of 2 times the damping ratio. And so that's just a way of locating where our inverted V starts. Our inverted V always has 20 dB roll off on either side, high frequency side or the low frequency side. As you underdamp this more and more, this becomes narrower and narrower, at least relatively looking relative to our response. Within the limits of my artwork, we get a fairly narrow 3 dB passband range. That's 2 arrows on both that side, so that would be a very narrow band pass filter, which is usually what you would build. And so, back in the old days of car stereos, you would tune the stereo by rotating the dial, which would effectively change the passband. Not mechanical anymore, but in the old days it was. There'd be a little pod in there. Filters, all these things were built analog. Now they're all done digital. It'll come back. Stuff always goes full circle. So these are the things we talked about in the last class. Any questions on this? We did an example in the last class. This was reviewed. Now to do a general comment, for our second order circuits, without looking at the circuits themselves, a low pass filter H of S always takes the form omega naught squared, S squared plus 2 alpha S plus omega naught squared. This is regardless of the damping. So that will be the form of the transfer function. That's a low pass filter by definition. A band pass filter, H of S, 2 alpha S, over S squared plus 2 alpha S plus omega naught squared. High pass filter, H of S, S squared over S squared plus 2 alpha S plus omega naught squared. These are things that you probably want on your crib sheet. So these are the transfer function forms. Whether you're building a low pass filter, band pass filter, high pass filter, depends on the circuit and what you're measuring across. For our familiar RLC circuit, the low pass filter is measured across the capacitor, the band pass filter is measured across the resistor, and the high pass filter is measured across the inductor. But these are the general forms of the expression. So if you're building a high pass filter, this is where you start, but you need to know how to translate this back to a circuit. If we're looking at RLC circuits like we have so many times, we know what this is. So if we're looking at RLC series, omega naught squared equals 1 over LC, and alpha equals 1 over 2 R over L. RLC parallel, omega naught squared, also 1 over LC, and alpha equals 1 over 2 RC. And those are things we should be familiar with, though, again, this slipped up a lot on the last exam. So make sure you get that right. We could have any other circuit, though. This is the RLC series in parallel that we spend so much time with because they're fairly straightforward to analyze, but in general, omega naught and alpha depend on the circuit. You gotta go to the transfer function building, find out what alpha and omega naught are, translate that back to circuit properties, of course. But ultimately, every second order circuit falls into one of these three categories if we're just measuring across one component. All right, one thing we haven't looked at here is the phase. Everybody okay with this? Got the notes if they want. Phase of our second order circuit. And again, overdamped, same as homework 8. Find the poles, find the zeros, everything's real. You cross a pole, what happens to the phase? The phase changes by 90 degrees. Approximately how? Over 2 decades, one below, one above. So for a single pole, you do something along the lines of this. There's our pole, maybe that's 180 degrees, and that's 90 degrees. So we have a change of 90 degrees, spread out over 2 decades. We call this pole 1 over 10, and that's 10 times pole 1. That would be 2 decades, 2 orders of magnitude. So we spread that over, critically damped, and you repeat that for both poles. Critically damped, nothing different. Again, same as homework 8. So what else do we have to have? We still have to have a first order circuit. So we still have our RC circuit. That hasn't changed, and we still need isolation. And we're underdamping the circuit. And it's still low pass filter, so we measure across the cap. But what are our defining equations now? Well, omega C of this guy, 1 over R1, C1 is still 10 to the 8. It hasn't changed. That pole has to be there, that's a real pole. And what is that going to give us in terms of our corrections to our straight line approximation? What does this contribute? minus 3 dB point relative to the passband at 10 a day. Which means this has to give us what correction? Minus 1.5 dB. Because this guy's fixed. We have that first order circuit that's going to give us minus 3 dB all the time. And so we need minus 1.5 dB here. Well, without doing the math, is the damping ratio greater than 1/2 or less than 1/2? So this winds up being minus 1.5 equals 20 log. Let's go over 2 times the damping ratio. In order for that to be negative, what must be true about the damping ratio? I'm not sure I quite heard what you said, but what must be true about this argument for this to be negative? It has to be between 0.5 and 1 to answer the ultimate question, but this has to be greater than 1 for this, this has to be less than 1 for this to be negative, which means 2 delta is larger than 1. And going back to the original question, delta is between 0.5 and 1. The only reason I bring this up is where was our metric? What's our 0 dB point? So we would get 0 dB correction relative to the passband when the damping ratio is what? 1/2. So we saw that earlier. That's our boundary between when our correction goes above 0 dB or is between minus 6 dB and 0 dB. So our damping ratio 0.5 to 1. Our correction is still negative, but increasing as we underdamp more and more. And so we can find what our damping ratio is there. We can write that as 20 log omega naught over 2 alpha. That gives us one of our expressions, and then our other expression, just write it up here. Omega naught equals 1 over square root L2 C2. And we can plug in omega naught and alpha. Omega naught square root is 1 over L2 C2, and alpha, of course, 1 over 2 R2 over L2. Didn't give myself much room there. We know what that is. That's for this series RLC circuit, of course. And to emphasize, this is underdamped. So for that triple pole to be larger than minus 9 dB, we have to have an underdamped second order circuit. How much it's underdamped? Well, that depended on our spec and the fact that we have minus 3 dB here. Just to posit something before we do the team assignment. If we look at the same thing, low pass filter, we can say I made the cutoff 10 to the 8. 80 dB roll off. And we have at omega C minus 6 dB point relative to the passband. How could you build this with just second order circuits? What would you do with your second order circuits? You have choices. So effectively, what is that? So if you did one with no correction, so minus 6 dB, or plus 6 dB. I'm not sure what you mean by no, but one with 0 dB correction and one with minus 6 dB correction. Effectively, what have you built? So we can do 2 second order circuits. So this can be 0 dB, which makes this what? Negative 6 dB. What's this circuit in terms of damping? Critically damped. What's the damping ratio of this circuit? We just said it a minute ago. The damping ratio is 0.5, 1/2. What about 3 dB and 3 dB? Those circuits are both underdamped with a damping ratio of 1/√square root of 2. So these are in our ballparks. These circuits would be exactly the same. What about this circuit? They're both underdamped. And if we really felt like being stupid, 4 dB minus 12 dB. Yeah, I know. This guy would have to be overdamped, and then this guy strongly underdamped, and it would look a little bit messy. Yeah?
Is there a reason why you want correction? Like in practical applications?
You always want a maximally flat passband. That's the whole point. So you want a maximally flat passband, but if you did 0 dB and 0 dB, then you also get a bump in the passband. So you're never going to get this. That's the goal. Now, ultimately, higher order, is that the wind? Higher order filters, we're going to build, or in practice, you build more or higher order than second order filters. You have much more sophisticated filters. And they actually look something like this. You get a response that looks something like this. And a very steep roll-off. And there's a whole collection of poles and some zeros in there. So this is an nth order filter. Poles and zeros, steep roll-off. You know, 7th order filter or something like that. And the variation in this region, in this oscillation, that's a 3 dB variation. That's a design criteria, because that's been kind of agreed on. That's an acceptable range of values. So that's a 3 dB variation of these poles and zeros as things kind of go up and down, and that's acceptable. And by steep roll-off, I mean maybe 180 dB. That would be a 9th order filter, 140 dB per decade, 7th order filter. These are real things. And if you go to the Wikipedia page and look up Chebyshev filters or Butterworth filters, it gives you information about, you know, the higher order filter designs. It gives you what the poles are relative to the normalized plots. And a reasonable thing to check out. All right. Good time for a team assignment. We will have some discussion after that about a couple other things. Like this. That's 10 to the 4, that's 10 to the 6. This was 40 dB per decade roll-off. That was 20 dB roll-off. And since I saw this a lot, and I know a lot of you know the answer since you all shouted out, this continues on to where? Infinity, beyond Schenectady. So, out to Hawaii and beyond. But you're missing a page. So, what does that mean? We have a zero where? Well, this is a slope of plus 20 dB per decade. We have a zero at 0. Zeros at 0. What order of 0 is it? Single, double, triple, quadruple? It's a single, 20 dB per decade slope. That's our starting slope. As an aside, if we had a minus 20 dB per decade slope, what would that mean? You have a pole at 0. Can we build something like that? Not really. With active components you can, but not with just passive components. So we have a 0 at 0. Most of you got this right. We have a pole at 10 to the 4 and 10 to the 6, a double pole. If we write this out now, we could say h of s equals. If we want, we could really be a little silly and write that s plus 0. That's our 0. 0 and 0. Why not? That works. I mean, the 0 is the identity operator there. S plus 10 to the 4 and s plus 10 to the 6 squared. Now, here we're making a little bit, I don't know what to call this term. It's not a gain term. What's the gain in this circuit?
0.
This was 0 dB. The gain is 0. Or, in other words, K equals what? K being our gain term. K equals 1. We can write K out front. K equals 1. There is another constant here. I'll just call it A for lack of something better to call it. What is that constant from? Well, it comes from part of the filter design. How do we find A? Well, if we look between 10 to the 4 and 10 to the 6, that's our pass band of 0 dB. H of s must be what in that region? It has to be 1. If this is a 0 dB pass band, we can define our regions. We can go back to the same thing we've done before. S less than 10 to the 4. H of s equals something. We don't care what that is necessarily. 10 to the 6. H of s in this case is what? Well, that's 1. That has to be 1. That's a flat or horizontal line at 0 dB, which means h of s is 1. 20 log of 1 is 0 dB. Well, going back to our transfer function, keeping the dominant terms, h of s is approximately as. There's our dominant term. S larger than 0, of course. Our dominant term between 10 to the 4 and 10 to the 6, that's S, and 10 to the 6 squared, which equals A S over S, 10 to the 6, meaning A is what? Squared. 10 to the 12. And that would round out our transfer function. So that would be our transfer function. This is one way of finding that missing constant. Another way is just to plug in some s. So you can go back to the transfer function and plug in 10 to the 5th. Why not plug in 10 to the 5th? I did this as a range, but if we put 10 to the 5th here, well, that's the dominant term. We get 10 to the 5th. 10, hey, come on, folks. We're almost done. There are people trying to listen and realize there's excitement brewing outside somewhere. So we can just plug in a number, find that missing constant. What does this bandpass filter look like? Well, effectively, what is a bandpass filter? Not where I was going, but if we break it down into parts, what type of filter is that? That's a high-pass filter. What type of filter is that? So we can build a bandpass filter with a high-pass filter plus a low-pass filter. Where you have to be careful, omega C low-pass filter is larger than omega C high-pass filter, right? It's off our plot there, but here's the cutoff frequency for the high-pass filter. There's the cutoff frequency for the low-pass filter at 10 to the 6. If we don't do it that way, we don't have a bandpass. Actually, if we reverse these, what would we have? Well, we'd have something that was a lot less than 0 dB everywhere, so it would be a stop all filter. Some parts would be less stop than others, but it wouldn't really be any type of filter. So, what are we looking at here? Well, low pass filter. This 10 to the 6 goes with which term? That's part of our low pass filter. That's part of our high pass filter. So we have a low pass filter with a double pole, which means we do isolation, isolation, and now what do? We have a high pass filter with a single pole, cap, and resistor, and you can do it with inductors or whatever as well. And what are these values? Well, if we do 1K here, we can do 10 to the minus 9, 10 to the minus 9, 1K, and 1K here, and 0.1. And those are all reasonable values. Oh, sorry. I was thinking inductor, right. So 1K, and now we what? 110 to the 4, so 10 to the minus 7. Forgot what I was doing. Apologize. So I was thinking inductors, and I stopped. All right. So yes, you can build it with inductors like other people did. Yes. Goodbye.